All right, so for the next few weeks, we're going to be looking at probability for the most part. So a lot of people have done stuff with probability and things before. Mostly you're working on it with playing games, rolling dice, flipping coins, cards, those type of things. Before I go into this lesson, I always have to ask this question. Is there anybody in here that does not know anything about a deck of playing cards? Good. Okay. That'll make a lot of these questions a lot easier because they do have a tendency to use playing cards as one of the problems that you need to use. So, all right. First thing we have to look for, we're going to look at some definitions. Random experiments. So whenever we're looking at probability, we're basically looking at an experiment. So a random experiment is defined as these three things. There is one distinct outcome for each trial of the experiment. So there is one outcome for every one. So if you flip a coin, I can only get heads or tails. I cannot get both. Okay. So every trial has to have one answer. The outcome is uncertain. So we do not know what's going to happen ahead of time. We can make a prediction. That's kind of what we're doing in probability and statistics anyway. But the outcome is still uncertain. We could still easily get it wrong. We do not know for an absolute certain that what the outcome is going to be. And the set of all outcomes of the experiment can be specified, and that's known as your sample space. So we need to be able to write down all the possible outcomes. It is possible that that can be a long list or a series, things like that. It does not necessarily have to say, like I can have a million different outcomes. That's possible. You're not going to have to write them all down, but it can be written down, and that's the point. So these three things always have to be true of anything that we're going to be looking at. So when we're looking at different problems later on, sometimes we have to go back and think, is this criteria true before we do the problem? An outcome. An outcome is any member of the sample space. So when I flip a coin, if it comes up heads, that's the outcome. An event is a set of the outcomes. It is not the same as a sample space. So if I flip 3 coins and I come up with heads and heads and heads, that is an event. All right. So let's look at a couple. Flipping a coin. Tossing a coin. Have we met? If tossing a coin doesn't meet the 3 criteria of a random experiment. So what was the first requirement? Yeah.
There's one distinct outcome for each trial of the experiment.
Okay. So is there one distinct outcome every time I flip a coin? Yeah. It's not going to land on the edge and get both. Like it's either going to be heads or tails. What's the second one? The outcome's uncertain. Hey, gentlemen. Shh. So we don't know it before we flip the coin. What's the third one? What was the third part of the experiment? Right. What's the sample space for tossing a coin? Heads or tails? You can do that. But when you're flipping a coin, typically it's heads or tails. All right, so that would be your sample space. So this is a random experiment. We're good. What about this one? Yeah. Okay. Yes.
There's more than one outcome though, because the 3 times it flipped.
So this is why I use this one. So I'm flipping 3 coins, or I'm tossing a coin 3 times and observing the number of heads. So the question is I'm tossing, okay. So when I flip the 3 coins, is that a single outcome of the event? Remember, the outcome is part of that sample space, right? And the event is a set of outcomes. So if we list, I'm flipping the coins 3 times.
Also, I think it's one distinct outcome because the like wording of it is asked just the number of heads, not the other options.
Yeah. So basically, if I flip a coin 3 times, let's go backwards. What's the sample space going to be? No, see, now that would make this not an experiment. If it was just heads and tails, that would make this not an experiment, because when I flip a coin 3 times, I'm going to get more than one head, or I can get heads, tails, and heads. I can get more than that. Okay. So when we're looking at flipping a coin 3 times, my outcome, the pieces of my sample space, have to encompass those 3 coins. Okay. Kind of. But we can't use 0 to 3 because those aren't going to be equally, each one's not going to have an equal opportunity of coming out. So we actually have to look at what the outcomes are. So I would have heads, 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 tails, heads, tails, heads, heads, tails, tails. So that would be my sample space. Because those are all the different outcomes I would get when I run the experiment. And every time I did flip the 3 coins, I would get one of those 8 outcomes. Okay, does that make sense?
This is all possible outcomes.
Yeah. So because like heads, heads, heads is a different outcome than heads, heads, tails. So either one of those would be like, that's how we can get around the having multiple outcomes or multiple possible answers when I'm flipping 3 coins, because the flips, the combination of those 3 flips gives me one possible outcome. Yes.
Are those kind of brackets like?
And they're squiggly brackets. They're for sets.
Okay.
So if you look on your keyboard, it's the ones right above the solid brackets, right above your, yeah. It's the squiggly brackets. We use them for sets all the time in math. All right. The only other one that we have to actually determine is would we know the outcome before we flip the coins? No. So this is an experiment. All right. Deck of playing cards.
Just clarify the previous one. If it asked about all the coins, not number of heads, would that be different or?
No, actually, in this situation, they'd end up being the same. So even though it asked the number of heads, these are the outcomes that we would get. The answer that we would say afterwards, we say, okay, we got 3 heads, 2 heads, those things. The reason why you have to list all of them like this is that there's multiple opportunities of getting 2 heads. So the probability of each isn't the same. So when you're looking later on down the line of trying to figure out probability, you need to have the separate options. Yeah. So. All right. Next one. So we have a deck of playing cards consisting of 13 hearts, 13 clubs, 13 spades, 13 diamonds. Drawing a card from a well-shuffled deck, observe the suit of the card. Have we met the 3 conditions of a random experiment? Does the card have more than one suit? No. So when we pull a card, it's going to have one suit. So therefore, there's one answer. Can we know it before we pull it? Yeah. Yes, if you flip them over, you can. Yes, this is going to be hard, but that wouldn't be an experiment at this point. So yes. All right. So based on making an experiment, we will not know the outcome beforehand. What is the sample space for this? Yeah. Yeah, we don't care about the thing. And there's an equal number of them, so we don't have to worry about that other thing like we were doing with the heads and stuff like that. So heads, clubs, spades, and diamonds. Good. Inspect the transistor to determine if it meets quality control standards. So everything we've done so far has been like a game, like dice, cards, coins. What about this one? Is there only one outcome? That's the first one. Yeah.
But this kind of is like pass fail or like a range.
Well, if we're asking if it meets quality control standards, it'd be pass or fail. So it's either going to meet the quality control standards or not, right? So there is only one outcome. It's either going to meet it or it's going to meet it or not meet it. So it passes it or fails it. Okay. So the next question is, do we know it before we pick it? No. We're uncertain of the outcome, correct? So the sample space for this one, we can list them. Would be pass and fail. And actually, even if it was a range, each one would still only have one of those options.
Right.
So even if it was a range of 0 to 10, for example, it still would meet that first criteria because it would only be one answer. Each one would only get that thing. So a great example of that is if you ever like collect baseball cards or comics or anything else like that, and you get them graded, they come back with 1 grade. So that would be a scale, but it would still be only one possible answer at the end. All right, good. Relative frequency. So there is, whenever we're looking at probability, there's 2 main ways to look at probability. Relative frequency, and you typically do not call them what Hawkes calls them. They're typically called experimental and theoretical. This is what's known as experimental. I do not know why Hawkes calls it relative frequency. But you're going to see it asked relative frequency in Hawkes. No, it's called relative frequency. Everywhere else in the world, it's known as experimental probability. You'll understand exactly why in 1 second. If an experiment is performed n times under conditions, this is going to tell you the probability of that event happening. So relative frequency, you have to do the experiment multiple times to determine the probability. Okay. You take the number of times that you want the event happened and divide it by the total number of times you've done the experiment. And that's all relative frequency is. Now we'll look at it. So, for example, if I flip the coin, oh, no, it's this whole thing. That's fine. If I flip the coin once, it either come out heads or tails, right? So in this situation, we're only going to look at heads. So if I flipped it 20 times, they got 8 heads. Okay. And the more they flip it, the more it balances out. Okay. So now we're flipping it 200 to 300 times. And you can start seeing it's getting closer and closer to that what line? The 50%, right? What should happen? If you were normal, just think about a coin. What is the probability of getting heads on a coin? 50-50, right? 50%. That is known as theoretical probability because that's what should happen. When we're doing an experiment, that is not always what's going to happen. Okay? I can flip a coin 100 times and get 100 heads. It is highly unlikely. Okay? And I'd probably figure out, like, go play the lottery at some point if that happens. But it is possible that that can happen. Okay? Or there's a possibility that when you're flipping, you can get a run of like 30 of heads in a row after you've gotten a whole bunch of tails and stuff like that. That can happen. As you get more and more of them, though, those things balance out, and you basically, it's known as regression to the mean, is what most people call it. We're coming up on baseball season. Baseball is a great example of it. So unlike every other sport where like basketball, football, hockey, things like that, there's not a lot of games, especially in football. There's only, I think it's 17, I think we're going up to 18 games. So there's only a set number of games. So you could have a player go on a run and just do amazing over those 18 games and totally outperform everything else that he's ever done. That's possible because it's a short season. In baseball, there's 162 games. It is highly unlikely that a player is going to perform insanely for 162 games. Normally, they will have massive run. They'll have runs, and then they'll fall off for a little while, and they'll balance out to that mean. That's what we're looking at here. When we're flipping the coins, a small amount of times you see it bouncing up a lot more, but once you get up into the thousands of times, it's a very small change. Okay, we're getting really close to that 50-50 shot in there. But this is relative frequency because this is looking at an experiment. We're actually flipping the coin that many times. Well, they're using a computer to do it, but we're actually still doing it. Yeah, absolutely. That's okay. Anytime you're doing probability, which is what frequency this is, it's what you want over how many times you've done it. So that K is what you want, and N is how many times you did the experiment. So, for example, the experiment was to toss a coin. We tossed the coin 1,450 times, so N is 1450. We got a head 718 times. So the relative frequency of this event was 718 divided by 1,450. And then we change that to a decimal, so we got 0.4952. Does that make sense? Okay. They call this the classical approach. This is theoretical. So theoretical probability is what should happen. We do not have to do an experiment for this. This is one of those things that we look at the actual total outcomes in the sample space. We figure out, okay, this is how many times this is going to happen. Okay. So for a coin, heads comes up, there's one head, and there's two total outcomes in the sample space. So the chances of getting heads is 1 out of 2 or 50%, 1/2. So the big difference between the classical approach and the relative frequency is we're looking at the sample space, we're looking at all possible outcomes, we're not looking at doing an experiment to determine that. So this is what should happen. There was actually a study done on, because at the beginning of a football game, they toss a coin to determine who gets the ball first, or they get to actually choose if they want the ball first. They actually did a study because there was enough coin flips over time with football things, and they actually found that it's not 50-50. They found there is a slight variance in the whatever one is on top when they flip it comes out slightly more often than the other ones did. And they don't know why, but because they've done enough games over the past 50 plus years that they have a large enough sample size that it's not coming out to be the 50-50 that they would expect. All right. So we looked at this situation. This is basically how I did the sample space for the heads earlier. So these are flipping 3 coins. So what is the probability? So we had, the question originally was how many heads, right? So what is the theoretical probability of getting 0 heads? Yeah. 1 out of 8. I have 1 out of, there's 8 possible outcomes right here. So that was my sample space. There's 8 of them. And only 1 of them has no heads. So my classical approach or my theoretical probability is 1/8. What's the theoretical probability of getting 1 head? How many of those lines only have 1/8? I think it's 2. Because that one has 1 and that one has 1. So it's 2 out of 8. Because again, it's always going back to out of my sample space. So 0, 1, 1. How many have 2? That's 2, 2. Oh, nope, there actually was 3 heads. There was actually 3. You were right. I missed that one. You're right. There was 3. There was 3. And there's 3 with 2. I'd have caught it in the end when I added them back up and didn't get 8. And then how many has 3? 1. So that is the theoretical probability of getting a certain number of heads when you flip a coin 3 times. Does that make sense? Okay. All right. So a gambler has made a weighted die. In order to decide which of the 6 sides is most likely to turn up, he tosses the die 33 times and notes the number of dots in the uppermost surface. The results of the experiments are shown below. So take this and find the relative frequency of each of the possible outcomes. All right, so what do we got? How many ones? All right, so 14 out of 31 or 33, which gives me what? Go ahead. Oh, you didn't get that one. What's the percent? You always need. So the problem is if you just give it to me as a numbers, it's going to be impossible to be able to compare it. Once we get them as actual percentages, that goes back to that being able to go look at 100. It's easier to compare them. So what's the probability of it? Yeah.
0.42.
Okay, so 0.42. All right, what about the twos? Okay, so 7 out of 33 is what? Okay. What about 3? Out of, so that gives me what? Okay. What about 4?
0.06 repeated.
Okay. 5?
Yeah, I got that.
Okay, and how? What's that one? And 6?
I got 2, which means we can just do the.
Okay. Does that up to 100? Let's see.
That's up to 90.
Okay, that's a rounding error. That's fine. All right. And what should happen? So what's the theoretical probability for this? If you're rolling a die, what should happen? Right, which would be what? 1 out of? Okay. So it should be 0.17 for each one. So did he create a weighted die? Yes. Which one should he bet on? 1. And he created a poor weighted die because he's going to get caught pretty quickly with that. All right. All right. Couple of the laws of probability. All right. Probability of 0 means the event will never happen. Okay. So, like they come up with the example of getting 3 heads on 2 tosses. Like that's impossible. When pigs fly, not impossible. As crazy as it sounds, not impossible. Probably very, very, very unlikely, but the probability of that would not technically be 0. A probability of 1 means the event will always happen. Okay. So 0 means it'll never happen. 1 means it will always happen. Both of those are equally very unlikely to be one that you're going to get. The probability of 1 helps out a lot because like we did here, when we added them up, we should have gotten 1. That was the goal. Like if you add up all the possible outcomes, you should get 1. All probabilities must be between 0 and 1. So this really comes into play when you're doing your divisions. If you somehow get a number that's bigger than 1, you probably flip the fraction. Okay? Your bigger number always has to be on the bottom. Okay, so it's always got to be between 0 and 1. And probability of law 4 is what we did when we added them all up. The probability of all the outcomes must equal 1. Most of these are very self-explanatory. But can't help you catch those little mistakes and whatnot there. All right. Oh, sorry. Add them all up. Basically, it's just the sum of them. The probability of A plus B all the way to the end. So, like when we did the coin, the die, we did the probability of 1, probability of 2, probably added them all up. We got 1, or just about 1, because we rounded them.
Yeah.
So there is a possibility when you round like that, you're going to get like 0.99 or 1.01 because you're rounding. That is possible. That's a rounding error. Don't worry about it. All right. A compound event. So a compound event is looking at multiple events, combining 2 or more events. So in this situation, it says the marketing director of Sports Illustrated believes that anyone who possesses an income of greater than 50,000 or subscribe to more than one sports magazine could potentially be a good prospect for direct marketing. Mailing, yes.
So just to clarify, this was asking for the probability of both, not or, right? Like the probability of both of them.
Not yet.
Okay.
That's not what this is. So you could do either direction, actually, which we're going to talk about in a second. So this one's looking at, compounding. We're taking 2 separate events. Okay, we're looking at the annual income is greater than 50,000. That's one event. And subscribers of more than one or more than one sports magazine. That's a second event. So a compound event is taking those 2 events and putting them together. How they interact with each other can vary. You can have an overlap like this, or you can have them be completely separate. You could have them one be right inside of the other one. That's also possible. Okay, so how they combine can vary, but it's taking more than one event and putting them together. You will typically see those drawn as a Venn diagram, which is what that little diagram down the bottom is. That's known as a Venn diagram. So a Venn diagram just basically uses circles to put things together and show their interaction with each other, how they're related to each other. Now the answer to your question. So there is a couple different ways that we can look at this. So when we're looking at the union of 2 events, that is typically your or. So it is A or B or both. Okay, so that's when they overlap and you're using the combination of all of them. That is known as a union. So this one you would actually write as A union B. And that's the symbol in front or in the middle, stands for a U for union. And that would be A or B. So if either one of those is true, it would be an acceptable answer. The other way we can look at it is the intersection. Looks like a little N for intersection. and this is the and. So this is the one that's included in both A and B. So when we say A and B, that would be the intersection of those two values, or those two events. The other thing we can have is the complement of an event. So the complement of the event is basically the exact opposite of it, which can be very helpful when we're looking at probabilities, especially if we're looking at a bunch of combined things. It might be easier to look at the things that we don't want and then just subtract from one. So the complement of the event is always going to be 1 minus whatever the probability of that event is. Okay. So for example, when we're looking at rolling a die, the probability of me getting a 6 is 1/6, right? Probability of getting just a 6 on the die is 1 out of 6. What would be the probability of me not getting a 6? 5/6, because it's 1 minus the 1/6. That is the complement. Right? So the complement is the exact opposite. So it's taking whatever you got and subtracting it from 1. All right. Now let's look at some problems. Anybody play roulette? It's actually the easiest game to look at for probabilities. So this is a roulette table. If you've ever been in the casino, the roulette's the one with the wheel, with the ball on it. So whenever you're playing any game at the casino, the probability has always got to be in the house's favor. Okay, otherwise they don't make any money. So there are 36 numbers on the table, 1 through 36. There is a 0 and a double 0. Those are green. The 36 numbers are split between red and black, 18 red and 18 black. Okay. So what is the probability of a roulette ball landing on a red pocket? So to do theoretical probability, what do we need to do? 2 things. We need to know all the possible outcomes, correct? And we need to know how many we want. Okay, so how many red dots are there?
Oh wait, you said 0.
There's 18 red. Okay, so 18 red. How many total numbers are on the board? There's 38. So it's 18 out of 38 is the probability of getting red. Okay? Does that make sense? So remember, whenever you're looking at probability, it's, unless we're doing an experiment, then it's just the total number of the experiment. But if we're not doing an experiment, we're looking at theoretical. It is the how many you want over the total number of outcomes that their possibility is. So there's 18 numbers that I want. There's 38 possible numbers. So it's 18 out of 38, which would be what as a percentage?
Wait, 4, 7, or as a percentage, 47.
Oh, we can do it as a decimal. It's fine.
3, 7.
So not 50-50. Close, but not 50-50. What's the probability of the roulette ball not landing in a red pocket? So this is, we're looking for the what? What was the term we were looking for? This is the complement. Okay, so we're looking for the complement of what we just got. So all we have to do is subtract that from 1. So not red would be 20 over 38. Or 0.5263. Okay, does that make sense? All right. If you ever bet roulette, when you bet in red or black, you double your money. So it's played as a 50-50. But it's not quite 50-50. That's where the bank makes their money. So you can sit there and just play black or red. If you play long enough, you're going to lose all your money. Might take a while. Huh?
You're right.
Yeah. It's like eventually, like a long enough time, eventually you're going to run out of money. It was funny. So I was playing at Foxwoods. Roulette's my game. I love roulette. So I was playing at Foxwoods, and this woman was betting basically all these points right in here, all the way down. And she kept winning. Every time the ball landed on something, she'd win. Oh, and she also put one between 0 and 00. So every single time she spun, she won.
She was increasing her odds by.
Problem was she was winning, but she was betting more than she was winning. So she was losing a little bit every single time. But she kept winning. So she was excited. I'm winning. She had no clue she was losing a little bit every single time that she was spinning. The roulette person, the one dealer that she was spinning, she's been here for 5 hours.
Paid for 5 hours a month.
Yeah, and in all honesty, she was having fun. Who cares? Like depending on as long as you're not spending like a ton of money, who cares? I used to take back before the casinos changed all the slot machines to actually like give you tickets, and you have to it was a nightmare. I used to literally walk around with like a bucket full of quarters. Walk around, throw a couple quarters in the machine, spin it. If I lost, I kept walking. If I won, I spend it again or take my money and walk away. Like I could go to the casino and spend 5-6 hours just literally playing with a roll of quarters. Like you can't do that anymore. Now the tickets just aren't as fun with that. So it's like you can have fun with it, but eventually you're going to lose the money. So,
Never done betting.
The key is to do it where you're to play with money that you don't mind losing. And most people, it's like, and most people, yes, don't have a lot of money just to lose. So
36, 37, 38, 20.
the zeros, these are your, that's your 38. That's basically known as the house bet. So all the other ones there, because everything's based on 36. But there's a 0 and a 00 there. That's where the house makes their money. Because that changes the odds to being 50-50 or exactly what you're going to get to a little less than that. We Americans play with the 0 and 00. Europeans actually only have 1. They only have a 0. They don't have the 00. So gamble in Europe.
So how do I win? Mathematically speaking.
Don't play.
Don't play.
There you go. I went to a math conference in Vegas once, and Bill Nye, the science guy, was the keynote speaker. He gets up, he goes, "Who thought it was a good idea to bring a bunch of math teachers to Vegas? They know the odds." I'm really good at blackjack, and I can win at blackjack. I don't play blackjack because I don't feel like getting kicked out of the casino though.
Yeah, if they're too good, they don't let you play.
Because I can count cards without even thinking about it. So it's like I just know it. It's just like it's there. So paid for my trip in Vegas though. All right. Odds. The last question that was on that thing. Odds are slightly different. If you ever watch like the Kentucky Derby or anything else like that, you'll see like the odds are like 20-1. It's 20:1 or 10-1 or 5-1, or if it gets down to like 1-2, they're basically the sure thing. So the odds are, for odds in favor, is what you want, the probability that it is occurring over the complement of it. Okay, so it's the probability that it occurs divided by the complement of that. So what you want divided by what you don't want, in essence. Odds against is the exact opposite. What you don't want divided by what you want. Did I do it on the next slide or did I have to go back? Nope, I got to go back. That's fine. I purposely do that after I do the other one because otherwise it gets really confusing. I wanted to do. Duplicate.
What was the against equation again?
I'm going to go back to it 1 second. There you go. And I lost it. All right, so it's just the flip. Where is the other one? Where did it go? There it is. There. Okay. So the odds of it landing on a red ball. So how many reds are there? 18. How many are not red? 20. So the odds of landing on red are 18 out of 20 or 9/10. You do not change this to a decimal. Odds are left as a fraction. Okay. So your odds are always going to be that. Perfect odds would be what? Huh? Yeah, it'd be 1. That'd be a 50-50 if it was 1. So like, what are the odds of me getting a heads on a coin flip? 1/1. 1 head, and there's 1 other outcome. So the complement to that is 1. So it's 1/1. All right. So what are the 4 laws?
The last probability law.
Maybe I didn't put the. Oh, 5 was the complement. I just don't think they were listed. They were marked. And I skipped 6 and 7 for. I'll show you the other 2, even though they're basically like I didn't put them because they're just assumed. Oh, actually, there's 6 and 7. So we'll put this there. There we go. All right. So 2 events that are mutually exclusive have no impact on each other. Okay. So they do not overcross. So that would be like pulling a jack out of a deck of cards and rolling a 6 on a die. Okay. Those are 2 mutually exclusive events. One does not impact the other at all. Okay. So those would be mutually exclusive. So 2 events that are mutually exclusive, I could add the probability of those together to determine the total outcome, to the total probability. Okay, so the union of those 2 would be the sum of the probability of each one. The intersection of those 2, since they don't intersect at all, would be 0. Those 2 make sense? So if 2 things do not overlap, the union is just the sum of the 2, and the intersection obviously is 0 because there's no overlap. If they do overlap, though, can I just add the 2 probabilities together? So let's say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 people, I think. 10, 11, 12, 13, 17. Okay. There's 17 of you in the room. All right. How many guys are there? 1, 2, 3, 4, 5, 6. 6? All right. So there's 6 males. What's the probability of being a male in here? Six out of 17 is what? I need it as a decimal.
35.29.
So 0.35. Okay. My second event will be wearing something black. So how many people in here are wearing something black? Raise your hand so I can count you. 6, 7, 8, 9, 10? Yeah. All right. So 10 out of 17 is what? 0.58, or so 5.9. So 5.88, right?
Yeah.
Okay, so 0.5. That's fine. So this is 0.35 and this is 0.59. So what is the probability if I was going to randomly select somebody that I would get somebody who is male or wearing something black? If I added those together, I would get 1. So 0.35 plus 0.59 is what?
Doesn't the fraction come up 16 over 17?
Probably.
If we had
Yes. So what's 16 over 17? 0.94. Okay. So that means if that's true, that means there's only 1 person in here that's not male or wearing something black. Okay. Is that true? Who's not wearing something black? I've got 2 males right now that are not wearing something black. And I got 3 people that totally that aren't wearing something black. So what's wrong with this? It should, but it doesn't. So what's wrong? There's overlap. How many males in here are wearing something black? If you're male and wearing something black, raise your hand. So there's 3. Okay. So there's overlap. Since there's overlap, I have to subtract that out. So when we're looking at these, this piece right in here, that intersection, I have to subtract because that's that overlap piece. Okay. So if the 2 things are not mutually exclusive, there's some overlap, I've got to subtract that out. Otherwise, I'm basically counting it twice. Okay. I'm counting it in terms of the males and I'm counting it in terms of something black. So I'm counting that person twice. So I need to subtract out one of them. Okay. So that's when we're looking at this type of thing. We have to understand what that overlap is. All right. Let's look at some problems. So the probability of A and the probability of B. Probability of A is 0.27. The probability of B is 0.19. If A and B are mutually exclusive, what is the union of A and B? So what's the probability? What is the union of A and B? Why? And why can we just add the 2 together? Oh, you're fine. Because they're mutually exclusive. That's the key. Since they're mutually exclusive, I can just add them together. What's the intersection of A and B? Because they're mutually exclusive, there is no overlap. All right, so we're back to that sports marketing manager. So the probability that somebody earns more than $50,000 is 0.2. So we'll say that A is 0.2. So this is 0.2. And B, the probability that somebody subscribes to more than one magazine is 0.3. So this is 0.3. They say the probability to find somebody in both categories is 0.08. So that's going to be the what? Not the union. That's the intersection. So the A intersection of B is 0.08. So that's in the middle there. That's the 0.08. So what is the union of A and B? So what's the union of A and B? So 0.5 is just adding the A and the B, right? Are these mutually exclusive? No. So we can't just add the A and the B. We're going to add the A and the B and then subtract off the what? The middle, that 0.08. So if we do add the 0.2, 0.3 is 0.5 minus the 0.08, we get 0.42. So it's the 0.2 plus the 0.3 minus the 0.08. So if they're mutually exclusive, we can just add them. If they're not, if there's overlap, we have to subtract off that overlap. Hold on, I gotta get the questions. Is this one right? Yep. Okay. What is the probability that the husband, so there's 1,000 policies here, okay? What is the probability that the husband will have between $50,000 and $100,000 of insurance? Yeah. Out of, yeah. So we're just looking at that. That's husband between 50 and 100,000. So it's 270 out of 1,000, which is 0.27. Okay. Next question. What's the probability that the wife will have between $100,000 and $150,000 of insurance? So we would be looking at that, right? Which is 80. So 80 out of 1,000 or 0.08. What's the probability that the wife will have more than $150,000 of insurance, or the husband will have more than $150,000 of insurance? So the wife having more than 150,000, or the husband having more than 150,000? Yes.
Is it 165 per thousand?
Why?
Because you can take the whole bottom row of the wife's more than 150,000 and the furthest right of the husband's, and then you subtract the overlap, right?
Right. So we're going to take those two, and then we have to subtract out that 15. We can't add it twice, or just add it once. So basically, we're looking at that. So that right there is your overlap. So these two events are not mutually exclusive, right? Because there is an overlap.
All right.
So so 165. Or 0.165. All right, let's see. All right, last question. Which approach do we use to this? What kind of probability is this? I'm going to go with the typical ones. Is it an experimental probability or a theoretical probability? Why?
Full numbers. I don't know if it's based on experience.
They chose 1,000 policies. So that, yes, if this is not like, we can't easily go, oh, this is going to work for everybody. Like, this isn't a theoretical thing. We took actual information and used it. So this would be an experimental probability or a relative frequency at this point, not a the classical or the theoretical approach. All right. That's it for today.